Welcome.
Hello, this is Team 97, and we are presenting a project on detection of AI-generated images and real images. So the data set which we are using is from Kaggle, and we chose this project because in today's world, the rise of AI is tremendous. The AI tools which are coming out on daily basis are tremendous. So we decided to classify if an image is AI-generated image or a real image. Then the data set consisted of about two folders. One is AI images and real images. They both had about 500 images each, and we did pre-processing of those images by resizing and rescaling them to a particular size for the model. Then we also did some few more uh, pre-processing techniques for our baseline model. Then the next part will be told by Vishnu.
So let me go over the baseline model. So we chose ResNet 50 as our baseline model. It is a popular model for image classification. The architecture of ResNet 50 is in the picture below. So 50 in ResNet 50 actually stands for the number of layers in the network, out of which 48 are convolutional layers, followed by one average pooling layer and one fully connected layer, as seen in the picture below. So the base model we used in our previous phase, we were able to achieve a 58% accuracy on the validation dataset. And that was the number we had to beat in our final phase. So going over pre-processing techniques we used on the images before we actually went to building and improving our model. So first thing is we added pixel normalization. We brought the pixel number between 0 and 1 by normalizing it. We resized the image to a fixed size of 224 because our data set has different sizes of images, not 224 only. So we resized all images to 224 cross 224. We did random image flipping and rotation, and we also converted the RGB pixels to grayscale pixels for better training. So coming to the improvements on the baseline model. So we added the following layers on top of the baseline model, that is ResNet 50. So first we added a global average pooling 2D layer. So this was added to reduce the spatial dimensions of the image by computing average of each feature map. Then we added a batch normalization layer. This is used to stabilize and speed up training. It just normalizes the output of each layer by adjusting and scaling the activations. And this helps prevent any sudden rise or fall in the gradient. This generally overall improves stability and quickly converges the training process. So it enables faster training and improves general performance. We also added dropout layers to prevent overfitting. And of course, we added a few dense layers in between with a radio activation function to connect them and also bring down the number of neurons. And we also had a final dense layer with a softmax function, which gives us the final output of which type of image was the input. And the activation functions were actually chosen based on trial and error. So we tried different types of activation functions, and this was the best performance we could get with these activation functions. So the results will now be explained by my teammate Mohit.
Yeah, so as we can see on the left side, we have our accuracy for the baseline model, which has about validation accuracy about 59%. And after making changes to our baseline model, as told by my friend in the previous slides, we were able to achieve the validation accuracy of 84%, which is of our final model. So we have these here F1 score. F1 score is commonly used metric for evaluating the performance of classification models, which is nothing but the harmonic mean of precision in recall, and which makes it useful when both false positives and false negatives are important. So so our F1 score is also about 84%, which is in line with our final model. I think that is much.